In this lecture, we'll talk about how to draw the electronic energy levels of an atom and add the electrons to it in the proper order. We'll follow the Aufbau principle and Hund's rule to draw the correct orbital diagram for a neutral atom and then decide if it is diamagnetic or paramagnetic. Let's begin. Energy level diagrams are graphical representations of the subshells of an atom. Here we see that each orbital is represented by a short horizontal line. Orbitals in the same subshell have the same energy. They are called degenerate orbitals for this reason. Notice that we start with the lowest energy subshell in orbital, 1s, at the bottom of the diagram. Then we list the other subshells higher up, depending on how much energy is associated with that particular subshell. When filling the diagram with electrons, we must observe the Aufbau, or building up principle. This means we'll add electrons to the lowest energy orbitals first, starting at the bottom of the diagram. We must also observe Hund's rule, which states that electrons within a given orbital remain as unpaired as possible. These unpaired electrons must also keep the same spin, so we usually fill the orbitals with electrons spin up before pairing electrons with their spin down counterparts. Let's work through some examples. If we look at neon, we see that it has an atomic number of 10. This means it has 10 protons and 10 electrons in a neutral atom. We'll fill the orbitals like this: 2 in the 1s orbital, then we move up and add 2 electrons to the 2s orbital, then we fill in the remaining 6 electrons in the 2p orbital. When we fill in the electrons, we show them in the lowest possible energy levels first because we're assuming they are in the ground state, which is the most stable. It is possible for an electron to be promoted to a higher energy level or an excited state, but we'll save that discussion for another time. Elements with no unpaired electrons are diamagnetic. These are not attracted to a magnetic field, but are very slightly repelled by it instead. To help me remember the term, I think of elements with all their electrons paired as being overly dramatic. I'd rather die than be attracted to you, magnetic field. Diamagnetic. Neon is diamagnetic. If we look at oxygen, we see that it has an atomic number of 8. So the neutral atom will have 8 electrons to place. We'll fill the orbitals like this: 2 in 1s, 2 in 2s, 4 in 2p. Oxygen is weakly attracted to a magnetic field, so we say it is paramagnetic. This attraction happens because paramagnetic materials contain unpaired electrons that align with an external magnetic field, creating a weak attraction. I emphasize the para and unpaired because it would be all too easy to think para and paired electrons go together. They do not. As we can see from our energy level diagram work here, oxygen is paramagnetic. If we look at carbon, we see that it has an atomic number of 6, so we have 6 electrons to place. Note that as I'm filling these orbitals, I'm filling each orbital with one unpaired spin-up electron before going back and pairing them with a spin-down electron. You do this for all degenerate orbitals before moving up to fill the next higher energy subshell in the diagram. When we're done filling the electrons in for carbon, we're left with 2 electrons in the 2p subshell. Because both are spin up, we say they have parallel spins. Starting with the 3rd and 4th shells, the energy levels of the subshells begin to overlap. For example, if we track the 3rd shell, 3s, 3p, 3d, we see that the 3d subshell gets tucked in between the 4s and 4p subshells of the 4th shell. There are 2 ways to remember the subshells in order of increasing energy rather than trying to remember the details of this diagram. The first method is to use an orbital filling diagram. You first list the subshells for each principal energy level, one line per principal level. Then you draw diagonal arrows pointing down and to the left through the sublevels. The order of the arrows is the filling order for the subshells. The second method involves reading the periodic table from left to right like a book. The trick is to realize that the first row of d orbitals occurs in the n = 4 row. But we know that our first d orbital is a 3d, so the d block of elements requires that you take n-1 to get the right principal quantum number. The f block has a similar issue in that you must take n-2 to get the right number, as the f block of elements is tucked in right here and continued below so that the table fits on one page.